All right. Okay.
Good, good. All right. Do you know, are we, I know you usually have to upload the
We are
video from the
caught up.
meetings. Are we current and up to date? Do
We
you know
we
if,
are we are
okay,
completely current and up to date, and it now says HamSCIence Telecon on the page, and yes, everything is up to date and uploaded.
awesome. Great. Thank you very much. That's good to know.
You're welcome.
Usually if we get behind a week or two, somebody usually asks and it's been quiet. So I figured we were good. So.
Mhm.
All right. What I'd like to start with today is just a kind of a cleanup from our previous year and a half worth of our efforts on getting the SCQP rolling. So let me do a quick screen share and show everybody where the results are at, and then everybody can chase them down if they want to see them afterwards. But here goes. Let's see how we do. Desktop. Okay. All right. So on the HamSci homepage, our first quick link now. And our first news item, which I just posted today, is our SEQP contest results. So if we go there, it's a pretty short article. I copied the formats from 2017 because if what works, why change it? We've got our top 3 winners. This stuff was announced at the HamSci banquet, and again made notice at Dayton HamBench. So there's nothing new there. But what is good, and I think what I'm kind of proud of, is we've got the complete results now. There is a multi-page document. I don't know, it's close to 30 pages now. So we've got some of the same statistics that I've had in the past couple of presentations. Let's see. Of course, the top 3 scores. We've got all the single op scores now are listed from top to bottom. There's many pages of those. The multi-op folks follow that. And with all the operators, so we've got good information there. If people want to look themselves up, see how they did. And of course, the check logs and the folks that came in from the various QSO parties that we wanted to recognize are listed here as well. So we've got that taken care of. And then, of course, credits. I know some of you have heard this before, but of course, Ed, Mackenzie, a lot of work on the publicity. Darsh and Cam helped me with the scoring quite a bit. Bruce Horn, WA7BNM, who's very well known in the contesting world because he supports probably a couple of hundred different contesting activities, including all the league contests. So far as log uploaders and certificate generation. And Bruce is also partially funded by a group called the Worldwide Radio Operators Fund, who maintains, I think, the CQ contest now that CQ magazine is, I think, defunct. And if they want to recognize you too, not only as the HamSci founder, but as the creator of the SCQP concept, I think we've carried that forward pretty well. But we wouldn't have a concept if we hadn't started with you. So thank you for doing that, of course. And then everybody, many of you on the call who've helped us with podcasts and club presentations and all that sort of thing too. We had a lot of people helping get our news out. And then we asked people to send in photos. There's a few photos on there. There's the Flark, the guys in Fairlawn. There's some of Ed's QSOs from last October.
Yeah, and I'm going to give out the award tomorrow night, by the way, at the club
Good,
meeting.
good. And everybody's soapbox comments I brought in, nothing super exciting there. And then we asked people to submit station diagrams. Some people made some very nice diagrams so we can see what kind of equipment they're running and how things are configured and so on and so forth. So I think it's a fairly complete wrap up. So if you're interested, take a look at that and see what you think. And if you have comments or constructive criticisms, let me know because I'll be doing another one in about 6 months for the April event. So no question about that. Okay, so that puts the wraps on at least the October version of the SEQP, and the GSAC was scored some time ago. So we're pretty caught up through 2023, I think. Let's see. Why don't we jump into Steve? You got some results on the TDOA, and that certainly fits into the science theme. So if it's okay, I'll turn it over to you, Steve, and we'll see. Let things go.
Okay. Let's see here. Can you see this stuff here?
Yep.
Why does it always, without fail, the little black thing that covers up the little things that you got to click on? Okay. So we have gotten a few results just as a quick reminder, the idea behind the time difference of arrival was, we know that multiple modes can exist, like 1 and 2 hops off of the F2 layer, come up here, come down off top E, go back up, lots of different modes. And we did see what we think are 2 distinct modes. This 1 and 2 hop off of the F layers are primarily one. Our goal was to see if we could see a change in layer height caused by the eclipse. And if you could do a true time of flight measurement, you know, just measure this time of flight, well, yeah, you could get this length very accurately, and then function of height, you could figure it out. But the problem is, to make TOF, you got to have absolute time standards like WWV on both ends, GPS DOs. That's hard to do. Easier to do is if you can measure the time difference of arrival between 2 modes, like 1 hop and 2 hop modes. Well, they follow formulas just like time of flight does. For example, here at 230 or so kilometers, the difference between 1 and 2 hop modes is 0.67 milliseconds. You go up to 300, it's 1.1, so on and so forth. If you know ground distance and you can measure the time difference of arrival between 2 modes that you can recognize, then you can infer what layer height is. So how do we sense that? We have three waveforms. We send out just some real short 1-cycle pulses. That's easy. You just look for the time difference between them. Sometimes that works. Sometimes it doesn't. Depends on receiver ringing characteristics. Another one is a pseudorandom noise burst, and we've been using those extensively. You can analyze those by correlation and autocorrelation, and it will tell you if that waveform has repeated itself, what the time difference is between them. And finally, we send these little chirps, linear chirps, linear sweep chirps. So if there's 2 of them, one of them takes the long path, one of them takes a shorter path, you know, like one's 1 hop, that's short, one's 2 hops, that's longer, so it takes longer, and they both arrive in the receiver at the same time. Well, then they get there with the time difference. And with the linear chirp, you get a beat note. And the beat note is the time delay times the sweep rate. So it puts this little modulation pattern on there. And if you measure either period or beat note frequency, you can back out what the TDOA was. So that's the basic idea. You can measure these yourself. For example, here's an actual record. This is using period. Here's Audacity. You highlight, for example, one cycle, and the peaks aren't so good to use because they're heavily modified by the AGC characteristics and audio passband characteristics, but the nulls are pretty good. So in this case, we highlight the difference between 2 adjacent nulls. Better if you go over more and divide by n, you get more resolution. But in Audacity, you set yourself up for start and length of this selection. So it tells you how wide it is. Down here in the bottom, you see it's 0.051 seconds. And then you can, all this stuff, I gotta get it out of the way so I can see. There we go. Beat notes, TDOA times sweep rate. If you can measure either period or frequency, you can back out TDOA by the beat note frequency divided by 10. It's because we're 10 hertz per millisecond, or 1 over the period times 10. So in this example, we got 0.051 is the length of time between these 2 nulls. Multiply by 10, take the reciprocal, you get 1.96 milliseconds. So this waveform is indicating a time difference of arrival of 2 different modes that arrived 1.9 milliseconds apart. So, okay, there we go. That moved to the next picture, it looks like. Here's some of the data that we have taken. This one on the left is the 1 and 2 hop mode calculated manually by that method I just described. I looked at each and every chirp, picked the best one out of the bunch. It had the cleanest pattern, measured that period, converted it to layer height, and overlaid it on this HMF2 record from the Austin ionoson. And we did see a peak up at around 18 Zulu. Our local eclipse max was really at 1830, so it preceded it by a little bit. But what I was happy to see was that, heck, our height calculations were right in with what Austin ionoson said HMF2 was. So this shows not only a peak, but it also shows that by golly, we can measure height too, and it worked. Over here now, short and long is sometimes we saw a peak, sometimes we didn't. It depended on frequency and a few other things. Over here is decoded data for 7 megahertz on 40 meters. And both of these were, by the way, on a short path. My neighbor Sam is only 9 kilometers away, so this was a Nevis path, almost straight up, straight down. This is what 60 meters looked like. On 40 meters, we did not get a height bump at eclipse time, but we did get a height measurement, which really, by golly, pretty closely tracked what the Austin ionoson said the height was. Oh, and by the way, the Austin ionoson didn't see a height bump either. In fact, most of the ionosons up and down the East Coast didn't. Interestingly, the Boulder ionoson, way the heck out to the west, did show a very prominent localized height bump at about eclipse time. So more two height bumps than meets the eye. Sometimes you see them, sometimes you don't. Same is true with the ionosons. Okay, here is, I've talked to you about analyzing these by looking at the period of that beat note on the chirps. You can also analyze the chirps and the pseudorandom noise bursts with an autocorrelation method. In other words, you take the waveform and correlate it with itself. And as you step it through itself, you can find the places where the correlations peak up. Tom, K1FR, did this autocorrelation analysis on 40 meters. This was the path from my location down here near San Antonio to Paul, N5DUP. He's 317 kilometers north and a little west of here. So the previous slide showed a Nevis path. This is one that's a lot farther away. The angles aren't straight up and down. They're spread out over more like 45 degrees. His analysis did show a height bump around 1900 Zulu. Our local max was at 1830, which would have been right here. This is one of the first results that we got. This is the TDOA over here in milliseconds, and here's layer height converted over here. Here's overlays of 7.3 megs, 40 meters on both the close path, the Nevis path, and the 317 kilometer path. The geometry here is very, very different, right? Nevis is straight up, straight down. Paul up in Abilene is 317 kilometers from San Antonio. But what's cool is those two data records just about lay on top of each other, which shows that, by golly, this thing worked over two different geometries, and they once again agreed really very well with the Austin ionoson over here. Didn't get a beat note, but by golly, we sure tracked the ionoson. And importantly, the Nevis path and the slant range path gave comparable answers. By the way, when you decode these by hand, it takes like a day. We do have some automated methods going on. I'm going to talk about those here in a minute. Here is that path up to Abilene, 317 kilometers on 7.3 megs. Here's the TDOA values. This is just spread out. It's not the whole 24-hour period. It's just during eclipse time. And I put this on here because this is what we got from the correlation measurements on the PN bursts, which show the E layer. Turns out this E layer may have been a big player in what we were seeing. And it's pretty close to what Austin said the E layer should be. We measured a little bit lower. Austin said E layer was 105. We measured around, more like 100. Still pretty close, maybe 97. And then Alex, case C3WD, I hope that's his call. There are two Alexes with different calls. I think one may be his dad, but I'm pretty sure this is him. He has compiled this data that's been calculated by all the analysis methods to include his automated measurement technique, which looks at beat note frequency. It actually extracts the envelope amplitude of that waveform you just saw of the chirp, and then does an FFT on the envelope. So he's using frequency, my manually decoded value used period. And here are two clocks. The one on top is 5.3 megahertz, and the one on the bottom is 40 meters, 7 megahertz. And they're clustering pretty close together. They don't agree exactly. Of course, this is HF. Why would they? But his overlays are pretty cool looking to me. The fact that they all more or less did the same thing is very encouraging. This little V here is the obscuration from the eclipse. Our peaks that we measured were not centered on maximum totality. They preceded it a little bit.
By how much?
About a half hour.
Huh.
1830 was the published totality, what they put on all the news stations here in San Antonio. This curve here that Nathaniel provided the code to calculate for it, and Alex calculated, it's pretty close to that. Here's 1832. And we were looking at more like 1800 for this peak. And it was measured by more than one method. It was done by the autocorrelation, it was done by manual period measurement, and it was done by the automated beat note measurement. And that was on 60 meters. No peak measured. In fact, there was a little depression here at the same time this had a peak on 40 meters. So there was a lot of complications, of course. This is the kind of pattern we'd like to see, nice and clean, well-defined nulls, very easy to measure. The nulls are better than the peaks. We have learned a few things, like don't trust the very first peak, because this little blip here, I intentionally made these chirps start with a 0 to full scale transition so that it would put this little impulse response on the wave file so I'd know exactly when the chirp started. These chirps go from 0 to 5 kilohertz. But these are radios with audio passbands. And the best we can do is like 100 hertz to 2900 hertz. So we can't see 5 kilohertz at the top end, and we can't see 0 hertz at the short end. When you start to see signal here is when the chirps have cleared the cut-on frequency of the audio passband. The lesson is that the shape of this peak is influenced not only by the beat note pattern, but by the audio characteristics of the radio. So this part right here, you can't trust. Going null to null is much, much better. We also had multiple modes present at the same time instead of one beat note pattern. You can see there's more than one in here. So we got some complexity going on. We also got intermittent washout. For example, here's a record. Now remember, it takes us, we're sending 10 of these chirps, and these are 3/4 of a second spacing, and then there's a 1.1 gap in the middle, and then more 3/4 second spacing. So from here to here is like 8 seconds. And in the span of 8 seconds, we got good beat note modulation, little less, washed out completely, and then it came back again. So you talk about rapid QSB, band was changing in a matter of seconds. This is a autocorrelation that shows how strong the E layer was. My impression was that the E layer could sometime let the rays get up to the F2 layer, in which case we could get our normal 1 and 2 hop modulation to give us this pattern right here. Sometimes the E layer was so strong, E layer happens first, so it's like a beam splitter. If it's so reflective, you can't get any energy up to the F2 layer, you don't get that modulation. But it can also return a signal from the E layer, let some through to the F layer, and now you got simultaneous E and F. And I think we got some of those. Nathaniel sent me this ray trace prediction that shows indeed here's an E layer mode, and this is about the right distance here up to Paul, 300 and some odd kilometers. Here's one hop off the F layer, same time, one hop off the E layer. So the ray trace programs tell you right up front, hey, you know, this mode is possible. So you can get this low ray and you can get this high ray. Okay, so I expanded. I use virtual height models because you get to use straight lines. And I don't have a ray trace program. I couldn't do it any other way anyway. Those aren't particularly linear because they're, you know, it's trig and Pythagorean theorems and stuff. But here's a summary of all TDOAs. Here's time difference of arrival down here. Here's virtual height over here for different ranges. Here's 250-kilometer range, 500,000, so on and so forth. The thing to notice is that at the ranges like from here to Paul, up there at 317, that's right in here, it doesn't get nonlinear until you get way down here. If you restrict your range from like, 275 to 350, it's pretty damn linear. It's pretty damn linear. So I replotted my predictions to include this is 2 hops off the F mode, interfering with 1 hop off the F mode. That's our normal 1 hop, 2 hop thing. But what happens, what would you get if you got 1 hop off the F and 1 hop off the E? Calculated that, assuming that the E layer down here was invariant at around 100 kilometers. And by golly, if you look at many onisons, that's pretty much true. When the E layer shows up, it doesn't change height much. It just hangs around at 100 kilometers or so. So here is an approximation of what the time differences of arrival would be for 1 hop off of E and 1 hop off of F. Notice that they're very much lower. These run from like, 1.5 to 2 milliseconds, 1 and 2 hops off of F. But if you get one off of F and 1 off of E, they're all very much lower. And by golly, we got some of those. Remember how fast and rapid those undulations were that I showed you earlier? We got a bunch of these where we got this really low frequency beat note pattern. Now, so low that I only got like 2 cycles in the amount of bandwidth that I had. If those 2 cycles happen to give you 1 null in the middle and 2 peaks, I really couldn't trust that kind of a measurement. But every now and then, the phasing would be such that I would get 2 nulls. Aha, that I can measure. So I did measure it. And by golly, if you take that measurement and go over here to this predicted graph, it came out right here. And it says, oh, you ought to be around 200 and something kilometers. And then you plot that on the Austin ionoson, it came out right there. So yeah, this is a guess and an approximation, but it's possible that this is the signature of 1 hop off of F and 1 hop off of E. And the reason I say that is that the higher frequency beat notes that come from F, they're gone, and it's been replaced by this. And the numbers came out right. So here is the long haul, the 317-kilometer path on 60 meters. This was the most difficult data set of all because I believe the E layer was so reflective that those things happened a lot. So the green dots are TDOA and the numbers over, since this is a, let me see here, TDOA over here, virtual height over here. Down here is the E layer. Here are those low TDOA values. And when you feed them through the formula I just showed before, they come up here. So they kind of fall in line. Now, over here, we got the 1F and 2F stuff when we got it. Sometimes we didn't get it at all because these chirps were just too washed out. And then we got these low ones that only had 2 cycles evident. But when you calculate those with the formula for 1F, 1E, they fall right in line with the others. So those are the reasons I think that we had 1F and 1E going on. So really, really, really interesting data set. One last thing that we noticed, sometimes the layer height can change really fast. I showed you it could change over an 8-second period. We also found out that it can change within the 3/4 of a second time it takes to send one chirp. And if the layer height is moving that quickly, it puts a Doppler shift on the chirp. So now instead of, and of course you get more Doppler on the second bounce than you do on the first. This is the same physics behind mode splitting that we've seen on the spectrograms of WWV, when you get, you know, one Doppler track and then one on top of it and one on top of that. More hops give you more Doppler shift. If we have one hop off the F layer, it incurs, and the F layer is moving quickly, we'll get a certain amount of Doppler shift. The 2-hop mode went up and down twice off of that layer, and it incurs more Doppler shift. Now you have differential Doppler, where the second chirp has more Doppler than the first. What does Doppler do? Well, it bunches up the waveforms, right? That's what Doppler is. It bunches the waveforms together. But the waveforms have a constant number of cycles. If you crunch those together, you also shorten the length of the chirp. So one effect of Doppler, if it happens during the time of one chirp, is it makes it shorter. Okay, it still goes from 0 to 5 kilohertz. But if it goes from 0 to 5 kilohertz in a shorter time, the sweep rate is different. In fact, if it's shortened, the sweep rate is faster. So I modeled that. I took one of the chirps, fed it through a wave program, told it to do a shift in pitch, and it did, and that made it shorter, and I exaggerated because I wanted to see the effect. And sure enough, now when you sum these together, you don't get a constant beat note. For example, here's a beat note, our normal beat note with a 2 millisecond delay, and you get this 20 hertz beat pattern, very, very regular. The time between here and here is the same as the time between here and here, same as here, same as here. But if you get Doppler that shortens one of the chirp lengths, your beat note shifts in frequency. It sweeps. You get chirp, chirp. You get a chirp on your chirp. The beat note sweeps because the sweep rates are no longer the same. And we did get some of these. Very, very interesting stuff. There's a minefield of just a lot of data to be mined here. Fortunately, those didn't happen all the time. Okay, that's pretty much it.
Why
That's
would it do
awesome.
that?
Do what?
Why would it do that?
What, the Doppler?
Why would the layer change so quickly? What's going on?
Good question. We have other data that showed one of the problems we ran into with the correlations was that the relative phase between when that pattern started and that start of chirp impulse that I put on there, so I knew when the chirp actually started, that changed. And the particular way that Tom was doing his autocorrelation, his indexing scheme was sensitive to that and exaggerated it. And so he had chirp, this 10 chirp sequence where each one apparently would change. So we saw a bunch of them where each successive data record, there was a skew in the chirp data. Then it got to a particular point where it's quit pointing to the left, had this little S-shaped curve, and then they started pointing to the right. In other words, they did a phase change. And that curve lined up with Nathaniel's sun angle curve. So the direct answer to your question is, I don't know. Clues might be that it's related to the sun angle. And of course, as a sun angle change, it's delivering different amounts of total EUV to sections of the ionosphere. So it's changing the ionization rate. I'm speculating here.
Yeah. So by sun angle, do you mean the sun zenith angle?
Yes.
Okay.
Yeah, in the morning, it's almost tangential, right? Sun comes up, and now the angle's getting steeper, steeper, steeper. At noon, it's pointing straight down, and then it goes shallower again. And it seemed to follow that pattern. Nathaniel kindly put that on one of his plots, and I says, "Oh, that looks like what our other data's doing."
So it's not temperature particularly, because the morning and the evening should be different.
I think it's ionization rate, the rate between recombination and ionization. I mean, what else would cause the height to change so quickly?
It ionizes a lot faster than the ion goes away.
Say that again, please.
It ionizes a lot more quickly than the ionization relaxes. So as soon as the upper atmosphere catches the ultraviolet after the eclipse, it's ionized again.
Yeah. We see that in the Doppler data, like from WWV, the morning spectra, when the sun is coming up, that's when all the mode splitting happens. It's a muck time. It's chaos. And then at night, when the sun just goes away and the ionosphere is left to recombine on its own, things are a lot more gradual.
One question I have is, how does the ionization in the D layer affect time of flight?
I don't know.
You might be measuring some of that.
Could be. And that's a question I've long wondered about, is what effect does ray velocity play in here? Because you can't tell the difference between a change in path length and a change in wave speed. And you know the wave changes speed or it would refract back to Earth.
How much is that change? Percentage wise,
What change?
the wave speed.
I don't know.
Okay.
But aren't there equations that relate wave speed and free electron density?
Don't know.
I think I
I think
remember seeing
it's
something
all
like that in
fine, right?
Davies.
Did you?
Well,
That's what's being
you said,
measured.
are there equations that relate wave speed and electron density? Is that what you asked?
Yes.
Well, yes. I mean, that's like part of the Appleton-Hartree equations, because that's what lets you do the numerical ray tracing.
Right.
you-
So what
You
percentage? does
you
the
can
rate
relate.
change?
You can
At
relate
what
the.
percentage does the speed change? 10%?
I don't remember.
Okay.
I'm not sure, but you can relate all of the electron densities to an index of refraction.
And index of refraction is the ratio of the speeds.
Right.
That's something that needs to be looked at.
I think as we continue to work towards getting the ray trace modeling up and more useful, I think there's a lot of power here to run some of these models that you're asking for. Because the ray tracing code will also tell you what the speed of the wave is through each point of the ionosphere. It'll give you all that information.
So it must go, let's see. Well, the refraction happens because the top of the wave overspeeds the bottom, and so it rotates over. Free electron density goes down, so the wave goes faster with smaller free electron density. Okay. So a really energized D layer would slow it down.
You do have to be careful because there's a difference between phase velocity and group velocity. The effective speed, which is the phase velocity, is higher further up, and that's how it refracts downward.
Right.
But it's the energy is not traveling faster. It's just that the wave effectively appears to go faster. So which one you're measuring that's a good question, whether you're measuring group or phase velocity in time of flight. I believe that would be group velocity.
Yeah, we pondered these same questions in
Yeah, see, the
2019 when we
thing
did
is,
that
group
time of flight
velocity
experiment.
group velocity always has to be below the speed of light. Phase velocity, on the other hand, can be effectively greater than the speed of light.
Right. That's what happens in waveguides when you approach cutoff going down in frequency. And I'm pretty sure that's why those ionoson plots asymptotically go up.
I think we are at the point where we can start giving Alex and Gerard the ray tracing code, because it is supposed the models of the ionosphere during the eclipse have been produced by Joe Huba, and then Devin Deal did set up the PyDarn or PyLab in order. Devin Deal made PyLab so it can take in those models and ray trace through it. And I think both Alex and Gerard are well capable of running those models and getting you the numbers that you want, which include the different, phase speed and things like that.
Very good question, David.
That's a really nice analysis though, Steve. I'm really impressed. Like I'm really impressed with how you were able to take those what look like outliers and say, okay, this is probably one hop F, one hop E, and then apply that formula and have it just fit right into the rest of the curve. That's really nice. And I think same thing with the Doppler analysis. That's also really nice. So I think you pulled out some really interesting things from that data set.
I saw several of these chirps. I mean, if you look at it, it looks like it's a regular beat pattern. But if you take those cursors and measure the difference between, the time between the first two nulls, 1 and 2, and then 2 and 3, and then 3 and 4, and then 4 and 5, they changed in a monotonic fashion. There was, without doubt, the beat note was not constant across the chirp length. Only way you can get that is if the two chirps have a different sweep rate, and you can get that from Doppler, because if it's descending, it gets shorter. If it's ascending, it gets longer.
Mm-hmm.
But which is interesting. It also gives you an error. But I think by looking at that chirp rate on the beat note, you can find out what the Doppler was and correct the absolute height measurement, if you were a mind to.
So what did you get for the highest level? What level did you get for the F layer to go between?
It didn't get much over 3. It was under 320.
And where did it start out at?
Well, here's one over here. This is the one where we measured on 60 meters. It looks like it may have peaked up around here, 315, 317, 320-ish. And it started out about 240 something, a little under 250. On this data set, on 60 meters. On 40 meters, it started out around 260. It peaked out around 305 or so, maybe 310. And then it came down for a while and then went back up again. Actually, I guess, use your imagination, this bump might be a eclipse-related bump. I don't know. Sure isn't much.
So if you have these actual numbers of, and suppose you just pick a frequency or wave like 60 meters or something, and so you have the two numbers for the F layer. If you look across the country at different places, does this go differently, or does it always stay the same? how many different data points do you have? You have 20 data points?
Each of these no, these are about 40 points across here.
No, how many different people?
Okay,
pairs
we
of
have
people?
in Texas 3. One of them's Nevis, one of them's at 317, and the other's at 365. I haven't started on the 365 path yet. That's Stan AG5HR. Took that data set. That was about the limit of these lower frequencies. Now, when you go to here to W3USR, and you're talking a 2,500 kilometer path, that really gets a lot more complicated because the TDOAs get much smaller. I mean, imagine a long, skinny path. All the bounces tend to get pulled together. So they all get less. The time difference of arrival between these modes is much closer together. And not only that, but you have to start worrying about takeoff angle. In other words, to make that one hop mode, if you're too far away, the takeoff angle from your transmit antenna is actually on or below the horizon. So you may not even get a pristine one hop mode. You may be looking at a 2-hop, 3-hop mode instead of a 1-hop, 2-hop mode. And we saved the 20-meter data till last. We do have several 20-meter hops. They're complicated by the physics things I just talked about. They're also complicated by the fact that we were QRM pretty severely.
Do you have any other people besides the ones in Texas that were sort of several hundred kilometers apart, pairs?
Gary, have people been sending in other data records? Has anybody else done this?
I haven't heard of any, Steve.
No, I haven't either.
Okay.
I mean, this took the whole day. We sat there from 9 o'clock in the morning until 2 o'clock in the afternoon, pounding these things out every 10 minutes. This was, not something you flip a switch and walk away from.
That was cool.
Took a pretty good time commitment from a lot of people.
So this ones you've just been talking about, was this the April eclipse or the one in October?
Both. We did it twice. We did the same thing in October.
But the ones you've just been telling us about now, this was all April?
Yes.
Okay.
We did get two. We haven't done as much analysis on the October eclipse. We have Tom's autocorrelation techniques. He did one on 40, one on 60. They both showed eclipse bumps. They didn't occur at the same time. They were displaced in time. Interesting. But they both showed bumps. We probably need to go back and revisit that data and do these other analysis techniques. We didn't have the Scranton automated processing online back then. I was crazy busy. First going through some other things, didn't have time to do all that hand analysis, but maybe we need to go back and do some of that.
This is really cool. If you go 2 slides back, when the solar eclipse totality and the HMF2 are there, maybe one more back.
Backwards?
Yeah, backwards. When we have 60 meters and 40 meter HMF2 values with the totality.
Oh,
not this one.
not that one.
Yeah,
This one?
this one. Yeah. So among these two, what is the difference between top and bottom? Because I got curious.
The one on the top
yeah.
is 60 meters, 5.3 megahertz.
Mhm.
And this is 40 meters, 7.2 megahertz. So different frequencies.
Okay, the trend here is totally different. Like
They're
when
different.
the eclipse is coming in, it comes down the HMF2 level, but for 7.2 megahertz, it's kind of constant or going up. So that's two opposite trends in two different frequencies.
This one also has the Austin ionosonde in it. This one doesn't. This one
Okay.
does.
Okay.
If you can pick that one out, it's this color.
Okay.
The Austin
And these are-
ionosonde didn't show a bump for the eclipse. Admittedly, it is almost 100 miles north of the path of totality. And our 60-meter Nevis path is directly under it.
Okay. And the one which is 7.2 megahertz that's over the long range of communication, or the range is nearly same for both 60 and 40 meters, the transmitter and receiver.
What does this say? I can't see the top of this graph.
Okay.
It's got a banner on it from.
I mean, the uplink and downlink, say the transmitter and receiver, the connection points, they
Yeah.
have the same distance at 40 and 60 meters, or they are totally different. From one is a lot more closer and others they are much wider over the geographic distance.
Okay,
Is
the
it?
top one, it says right here on the left. The top one is 5.3 megahertz, and it's a Nevis path, almost straight up, straight down.
Okay.
He was actually 9 kilometers away, just far enough away to where the direct ground wave didn't saturate his receiver. In fact, it was a perfect distance, actually, because we got good modulation between the direct ray and the one reflected from the F layer.
Okay.
Save making a directional coupler. And the bottom one is 7.2 megahertz at 317 kilometers. So that's
Okay.
that's what it tells you what the difference is over here.
Yeah.
So we saw these bumps at 5.3 megahertz in the Nevis path. We didn't see any bumps, at least not at this time. In fact, it
Yeah.
shows a depression on 7 megahertz and a 317 kilometer path. Those angles were around 45 degrees.
Okay, thank you.
Sure.
I really like this technique. I went through the PDF which you have sent long back when we were discussing about what is multi-mode. Now I get it. So I really like this technique and the way it can pull out the HMF to layer movement and even Doppler thing. So it is really cool.
One thing that we need bandwidth. Unfortunately, modern sideband radios, 100 hertz to 2900 or about 2.8 kilohertz of bandwidth is all you can get. Our chirp goes 0 to 5 kilohertz, so we lose the whole top half of it.
Okay.
Last October, I tried concatenated up-down chirps, but they went from 0 to 5, 5 to 0, 0 to 5, 5 to 0, and they did so with coherent transitions. In other words, at the very top of a cycle on the up chirp, it started immediately at that same phase point. But because it swept so far out of the audio passband of the radio, you got some data and then nothing, and then some more data, and you couldn't connect those two together. One thing we're going to try, if we do this anymore, is to do up-down chirps that are only within the bandpass of a radio, like from 1 to 2 kilohertz, or maybe 500 to 2500. In fact, I'd try 500 to 2500 first, because then you can let the time record stretch out longer and get more cycles of that beat note, which means you can see lower frequencies and get more precision on how you measure the high frequencies. And it would still not take up any more bandwidth than is legal in the ham bands. In other words, we're trading time for bandwidth. So got some ideas on how to make this a little better.
So you've got some ideas on how to improve the technique. Do we have to call for another eclipse, or are there other phenomena we may be able to use these to study?
Well, you've done such a great job organizing this, Gary. I was hoping that you would go ahead and schedule that for us.
Yeah. I don't think I have the budget. It's always an excuse.
I have an advertisement.
You have some advertisements?
So what do we
Yes.
say now? A word from our sponsor or what?
It's not exactly a sponsor thing, but maybe. So I have those eclipse curves that Gary, or not that Gary, those eclipse curves that Steve and Alex put on their plots. You can get them, you can calculate them yourself using the HamSCI Eclipse Calculator package, which is available in Python. And I put the link in the chat to this. And there are Jupyter labs that show you how to do these things. So if you look at the Calculate Eclipse Obscuration notebook, it shows you how you can put in a start time, an end time, a latitude and longitude, and you say you want to find what the eclipse obscuration is every 5 minutes. You can run this calculation and then you can plot your eclipse curve here. Similarly, I upgraded this code over the past week. You can now also calculate the solar elevation and azimuth using the same code. So again, you put in latitude and longitude, a start time and end time in UTC. And this is the solar elevation angle. So when it is highest, the most positive, that's local noon. And when it's the most negative, that's going to be local midnight. And then you also get the azimuthal angle as well.
That's cool.
You have, if you want to plot make these nice maps that have shaded paths of 90% eclipse or greater from the October annular eclipse, or the path of totality from the April eclipse. And if you want to draw on the locations of transmitters and receivers and the great circle paths between them, and also calculate the distance and azimuth heading from the transmitter to the receiver, this eclipse path maps Jupyter Lab will show you how you can do that. And you can just change some of the values in here from the latitudes and longitudes of the transmitters and receivers I've put in here. You can put in the ones that you want, and they can show up on this map. And then I also have a Jupyter Lab where you can create one object, which I call the solar context object. And you can give it a start time, an end time, a latitude and longitude. And then you can use that to overlay the solar elevation angle and the eclipse obscuration on a matplotlib axis object that uses date times on the x-axis. So this one, Eclipse Calculator code or GitHub repository, is available for you if you want to get information on solar elevation angle and eclipse obscurations. I think it could be very helpful in doing analysis.
Nathaniel, what sort of time resolution do you get, using that code? I'm not familiar with Python, and I certainly haven't looked at the code. So right now I'm just seeing examples of the graphs you're showing. But
you can put in an arbitrary time resolution.
Okay.
So here in this code, I've set it to a 5-minute time resolution, but really you can set it down to a much smaller time using the Python time delta object.
Okay, thank you.
So it could set 1 second or even, 1/100th of a second.
Yeah.
Under the
the
hood, it's using a package called AstroPy to do these eclipse calculations. So I'm not doing the calculations myself. I'm calling another Python code where some other people have very nicely done all of the math. But this is a really nice interface that makes it relatively easy to get the numbers you actually need for this particular use case.
Great, thank you.
You're welcome. And all the results are stored in, there's actually also a grid square converter in this package as well. And all the results are stored in pandas data frames, which are easy to export to CSV files if you want to use it in other codes or in Excel or something like that. that's my advertisement.
I wanted to share that Cam Kussing, who is, I guess, not in the call. Let me check if he's there. Okay. So he and I found out that there is a way to do the kind of plot which we have on the hand side. Let me share my screen, which is so this plot, it took 25 gigabits of or bytes of data file, which we needed to run it on the supercomputer. But with some dash data frame, we can run it on the laptop now, and it takes about, each frequency takes about 1 minute on 18 GB of RAM laptop, and now we can have them on the laptop for, say, each frequency about 1 minute. So in 10 minutes, we can have this figure. And we were trying to regenerate this plot, and we have been successful. And this is, let me say, no, not this one. Let's open the folder. Oops. Yeah, it keeps us here, right? So
So you're
yeah. So these are different frequencies which we have in the HamSCI Google page, web page, and this is what we have marked, the opening up of lower frequencies when the solar eclipse comes in. And so the good news is now we can run it on the laptop, which has about 18 gigabits of RAM, and that's how I'm doing it. And so I learned what the data set is and started to play with it. One thing which I also did was trying to do the same plot for different events which you have other in addition to solar eclipse. So one of them is a solar flare, X-class flare, which came on 14th May. These are from 9 to 14 was a very active day. You had a solar storm and there were lots of news. And this is a flare which was very strong, about 8.7. So about 9x9 plus, which is a very stronger flare. It should have some effect in the US continental region because it is happening around, say, noonish here. So if you look at this plot, okay. This is eclipse. Yeah, this one is it. So at this time is the flare. And this is first time I'm seeing this, but I guess it makes sense because at the time of the solar flare, D region should bulge up or it should have more density. So the amplitudes of the signals should weaken and they should not be received at other locations, or they should have the fainter intensity, or this, or maybe you guys might have seen this flare kind of impact. So this is where the flare is, and we see kind of almost no links are getting developed at the time of the flare because D region, I guess, is much more enhanced. So that's what I wanted to say.
Does that correspond with like an R3 blackout?
R3 blackout. I don't know what is that.
Well, flares cause blackouts because of all the increased absorption. And
Yeah,
that
yes.
looks exactly like it.
Yeah. So when I say D region enhancement, I'm saying the absorption of the radio waves in the D region.
Yeah.
Yeah.
Man, that is a very clear record showing that. I've
Yeah.
only lived through a few of those where I happened to be on the air at just the time that happened, and it was weird. It's like somebody just flushed the frequency.
Yes.
Whole
yes.
band just went quiet.
We just had a flare this afternoon.
Okay. Did not know.
WWV disappeared for a bit.
Wow.
Okay.
Well, Deep, that's really wonderful. And I'm
Yeah.
very impressed that you were able to use Dask to
Yes.
get that code to work like that.
Yeah, I really want to say if Cam was here, Cam really wanted to run it on a laptop. And
I don't.
so he and we kind of coincidentally discovered the same Dask dataset or Dask data frame, which can process these huge files on our laptop.
Wonderful. Do you know Bill Engel? You know Bill Engelkey, right?
Yeah, I had communicated with him over email. That's how I got the data.
Could you please tell him that exactly what you told us, that you're able to make these plots and reproduce those
Yeah.
plots using Dask, and only just tell him exactly what you told us. I think
Okay.
that's going to be very useful for him to know.
Okay.
And we should absolutely work on upgrading our code to use that same approach, I think.
Ah, nice. Okay.
And I'd like to, well, we've got two students who just walked in the room here.
Okay.
So one of them is a brand new Scranton student. So,
Hello.
Hi.
so here's Diego.
Hi.
Diego's on the other side of the Telecon. He used to be an NJIT student, but he's now a Scranton graduate.
Okay.
So he just moved here. And there's Kun. So I think I have to go because it's 5 o'clock and I have to go pick up Anthony so we can go to T-ball, and I have to talk to these students. But I think this was a really good Telecon today. So thank you for everyone. I guess no Telecon next week because of CEDAR. Or do you still want to have a Telecon even if I'm not on?
Mary Lou, what do you think? You want to wait or because
I don't know. What do you think, Nathaniel? Would you prefer to be here? Maybe we should cancel?
It doesn't matter to me. I just know I can't be there and Kuldeep can't be there.
Yeah.
But so all the CEDAR people can't be there, but you're welcome to keep going if you want.
Let's cancel it for now.
Sounds good. So no meeting next week, and we will resume the week after. And Kuldeep, I'll see you in San Diego.
Yep.
And Gerard's coming to San Diego too, and we'll see everyone in 2 weeks.
all right, have a good trip. Interesting
good
call
trip.
today, very interesting.
Thanks. Bye.
73 all.
73.